So in this recording, I'd like to continue the discussion on simultaneous linear equations, how to solve them using Gaussian elimination, and then also introduce matrix notation, which will make it perhaps a little easier to do the row reductions and just basically to write less overall. Okay, so to start out, let's review what the three operations, the row operations are. Number one is you can interchange rows. Number two, you can multiply an equation by a number. And you can multiply an equation by a number and then add it to another equation. And this last step here is really the key step that we'll be using to solve simultaneous equations. Okay, so as an example, let's say we have this system of equations, three variables, x, y, and z, with three equations. And so what we can do is we want to eliminate certain variables to simplify what the system is telling us. So what we can do is use the first equation here to use that to eliminate what this what that negative 2x is there. So what we're going to do here is we're going to take 2 times row 1, that's what this notation is about, 2 times row 1, and we're going to add it to row 2, and that will become our new row 2. So if we look at the third equation here, we can do 2 of these at once. Remember, we're not changing the first equation at all. We're looking at the third equation with a coefficient of 3x, so we can multiply row 1 times negative 3, and so that negative 3x plus this 3x will eliminate that x. And so we want to do that for every variable and the constants just to keep the equations equivalent to each other. So the first equation is unchanged, and so what we'll do is we'll take 2 times x and add it to negative 2x, and we get 0x. We'll take 2 times y and add it to 2y, and here we get 4y. And then we take 2 times z, or 2z times 2, and we get 4z plus z, and we get 5z. And then we'll take 4 and multiply by 2 to get 8 plus 7 is 15. So similarly, what we're going to do is then take negative 3 times x and add it to 3x, and we get 0x. Negative 3 times y minus 4y, and we'll get negative 7y. We'll take negative 3 times 2z, which is negative 6. Negative 6 plus negative 1 is going to give us negative 7. And we'll take 4 times negative 3 to give us negative 12, and add that to negative 2, and we get negative 14. So this is the first step in what we want to do, is we want to eliminate all the x's in the second and third equations. And so we really don't even have to write the 0x, and perhaps it's more clear if we do. So the next thing that we want to do is we want to now eliminate this 7z. Okay, so let me talk a little bit about the goal of how we're going to do this. So let's say we have a system of equations, and I'm just going to use symbolic coefficients here, a, b, c, d. No particular meaning to them at all, except that they're coefficients, but we have 3 variables. And so ultimately what we want to do is we want to eliminate these 2 x's, and we want to eliminate this y to get it into this form. So you can see this is taking this first equation, we have all 3 variables. Second equation, we have 2 variables. And the third equation, we only have 1. And so the strategy is to take that first x and eliminate all the x's below that, and then take the second y below the second this y here, which is in the second equation, and eliminate all the y's below that. And we can extend this then to do any number of variables. We just keep on going down the echelon and eliminate all the entries that are below this diagonal entry that we have here. Okay, so when we look at row echelon form here, we'll take this example, and if we add the first two equations here, this is another example. I'm going to do this one completely. So we're going to have add these two, and we eliminate that x. And then what we're going to do is take negative 2 times this x and add it to that, to row 3. And you can see negative 2 times row 1 plus row 3. And so we're going to end up with this system now. And I'll let you, you can push pause and check this for yourself to make sure you get the same answer that I do. But what I've done with this operation here is I've eliminated this x and then kept all the did the operation for the rest of the variables and the constant to keep the equation in similar form. So now what I want to do is eliminate the negative 3y, and so I'm going to take 3 times row 2, and you can see my notation, 3 times row 2 plus row 3, and when I do that operation, I get z equals 1. Now what we can do is what's called the back solve. So the back solve is basically using the second equation with the value of z that we have, which is 1, and then solve for what y is. And then the second thing that we do is we take our values now that we have for y, which is 2, and z, which is 1, stick them in the first equation, and then solve for x. And so we get our solution, x equals 3, y equals 2, and z equals 1. Okay, so let me introduce matrices now, and we'll do the same kind of row echelon solving that we did before, but we won't be writing x, y, and z and all the equal signs as much. So what we're going to do is look at what a matrix is. So first, a matrix is at its simplest just an array of numbers, rows and columns, and it usually has a rectangular shape like this. Notice that I have an entry of 0 here. In an equation, if we have like x plus z, we don't have to write 0y, but when we're using matrices, we always will write the non-existing or the 0 entries as 0. So we call this a 2 by 3 matrix, and we refer to that as its order. So its order is just its physical size. 2 rows, 3 columns. So this is when you're talking about the order of a matrix, it's a 2 by 3 matrix. Okay, so what we'll do with the matrices is translate our systems of equations like we have for this one here, and make it into we can take the coefficients here. You can see the 3, the 2, and the negative 1. So negative z, that has an implied 1 there. The 1, the negative 3, and the 1 here. And then the 2 and the y, just the 1 for the y, and the negative 2 for the z. And what I have here is just a coefficient matrix. And if you were to go on and study linear algebra, this is actually a pretty important matrix to use. The coefficient matrix, but we're going to use something slightly different. We're going to actually use what's called an augmented matrix, and what's different about an augmented matrix is that the last column has these constants that are on the other side of the equal sign. Now some texts will put a dashed line to show that these are variable coefficients and these are your constants, but that dashed line is optional. So I very rarely write that dash line. If you want to, because it keeps the meaning straight for you, that's perfectly fine, but there's nothing that says you have to. Okay, so just to reemphasize, we always have a 0 where a variable is missing. So if we had in that last equation just 2x minus 2z equals 3, we would definitely put a 0 in for the y entry. Okay, so what I'd like you to do here is find the coefficient and augmented matrix of this particular system. And so why don't you push pause and write the coefficient and augmented matrices the way I demonstrated on the previous slide. Okay, so after you do that, you can continue here, and you should get these solutions. Or actually, the second exercise that I want you to do is write the equivalent system for this matrix here. So now's a good time to push pause and to write out the system of equations that corresponds to that. Okay, so let's do this then. If we have the coefficient matrix would just be 3, -2, 4, 1, 0, -1, and -1, 3, and 0. So there's your coefficient matrix. Now your augmented matrix is going to have 4 columns, so that'll be 3, -2, 4, and 1. It'll be 1, 0, -1, and 4, and -1, 3, 0, and -5. And so that's your augmented matrix. Now the equivalent system for this system here would be 2x plus y plus z. See, I don't have to write 1 as a coefficient, equals 5. The second equation is 6x, and I can write 0y if I want, or I can just avoid that and write z equals 3. And then we have 2x plus y minus z equals, and the constant you always write in the system of equations. So you get that as your system. So that should agree with what you've come up with. Okay, so let's look at solving a system with a matrix we'll look at solving we'll be solving equations by using a matrix, and we use exactly the same operations that we used when we had complete equations. So we can swap rows, we can multiply a row by a constant, and we can multiply a row by a constant and add it to another row. Okay, so let's start with this one. If we look at what we want to do here, in this first one, we want to eliminate this 2, so we'll multiply row 1 by 2, and we'll or by -2, and we'll add it to the 2, so ultimately we're going to get a 0, and we do that for the rest of the operations. Now look what I'm doing here. I'm going to use the second rule here to change this 3, 9, -6, and 12. I'm going to multiply it by 1/3, and you can see what happens here. So I'm going to end up with, we take -2 times 1 plus 2, and that gives us 0. We take -2 times 3, that gives us -6, plus -1 gives us -7. And then we have -2 times 2 is -4 plus 0 equals -4. -3 times -2 is 6 plus 2 is 8. Now this row, what I've decided to do is just multiply it by 1/3. And so 1/3 times 3 is 1. 1/3 times 9 is 3. 1/3 times -6 is -2. And 1/3 times 12 is 4. So you can take these intermediate steps to make things simpler, because now all we have to do to get rid of that third row is to add, and I'll continue this, negative row 1 to row 3. And you can see that I'm eliminating that x. So the first two stay the same. And then now I'm going to add rows 1 and 3, where I'm going to take negative row 1 and add it to 3, so I get a 0. And then I take negative 3 plus 3, and that's also a 0. And then we have negative 2 minus a negative 2 gives us negative 4. And then the last one, negative 3 is 3 plus 4, and we get 7 there. And so here we're already in that row echelon form. Now, one of the things that we can also do is continue this and take these three values here and eliminate them and make them zeros. And what that'll give us is a matrix that just expands out to that you can directly read what the solution is. In other words, we can do the back solve within the matrix. Okay, so let me compare what we're doing here with these with this system of equations. So let's say I have this first system. I'm going to convert it into the augmented matrix, and so pause it and convince yourself that that's an appropriate conversion. So the first thing I'm going to do is add 2 times row 1 and add it to row 2 to eliminate that x. I'm going to work on row 3 at the same time. I'm going to take negative and the positive. And so I'll do the same thing with this matrix here. And you can see in my system of equations, I get those 2 new equations. And what you should do is pause it and check these operations so you get the same thing. And then my new matrix works out to be this. So if I take that third row, I'm taking negative 1 plus 1 is 0. Negative 2 plus 1 is negative 1. Negative 1 plus 2, and I get 1. And then I get negative 3 plus 1 gives me negative 2. So you can verify the second row yourself. And so let me look at the second row, and you notice that I have 5y plus 5z equals 0. So let's multiply it by 1/5. And so what I get is simpler equations, not doing anything to the third one. And you can see my matrix simplifies out. The third row stays the same. And now what I'll do is I'll say, okay, I'm going to... If you notice, what I have here is that the y here and the y coefficient here are additive inverses. So that was one of the reasons why I multiplied this by 1/5 to make this coefficient 1 and that one negative 1. So in other words, I adjusted it to make everything work just fine. And so I'm going to, from here, add row 2 and row 3, and I'll see that I eliminate this this y by 1 minus 1. Then I get 1 plus 1 equals 2. Here you can see this 2 here. And then 0 plus negative 2 is negative 2. And then I can do the back solve, and I get my solution of 2, negative 1, and or 2, 1, and negative 1. So in matrix notation, when I add those last two, I get 2 and negative 2. And we can, of course, do the same back solve. On this last one, though, what I'd like to do is, it says you try, but I want to take it through myself here. And I'm going to go a little bit faster. That what you should do is pause it to convince yourselves that I'm making the right choices here. I have 1 and negative 3, so I'm going to multiply 3 times this first row, add it to the third row. And I didn't have to do anything to the second row because I already had a 0 under the x, and so I have 2 zeros here. Now, what I'm going to do is I want to make these two work a little more nicely with each other. So I'm going to make this 5 halves, negative 5 halves times 2 will give me 5, so I can eliminate that 5. So it's negative 5 halves times 2 is negative 5, and that becomes 0. And then negative 5 halves times, we're doing row 2, so that's times 1 plus 7 gives me 9 sevenths. And then negative 5 halves times negative 5 is going to give me positive 25 halves minus 8, and that's 9 halves. Okay, so I can take this last row here and multiply it by 2/9, and that will give me my integers back, 1 and 1. Okay, so here's the back solve, and you should be able to do this pretty readily yourself. Or what we can do is keep going. We can take this matrix up here and say, I'm going to take, what I want to do is I want to eliminate this 1, and I want to eliminate this 2. So now I'm starting down here and eliminating going up the column. And so what I have is for the first row, it's going to be negative 2 times times 1, and so that eliminates that to be a 0. And then I have negative 2 times 1, that's negative 2 plus 1 is negative 1, and you can see what we have here. Then the second row, I'm taking negative row 3 plus row 2, and so this will eliminate this 1 in the second row. Now notice the numbers that stay out here stay the same, because when I'm multiplying row 3 by whatever constant, I'm not changing row 1 or row 2 because I have 2 zeros here. So 0 times negative 2 is still 0, so it's just going to keep those unchanged. Now I have one more thing to do. I'm going to, actually there's two things. I'm going to make this a 1, okay? So I'm going to multiply this by 1/2, and I get 1/2 times 2, and 1/2 times negative 6 is negative 3. And so then my last thing that I want to do is I want to eliminate in row 1 that 1 that corresponds to the y. And so I'll take negative row 2 and add this, and so I get negative 1 plus 1 is 0, negative 3 is 3 minus 1, and I get my 2 here. Okay, so why is this so nice to do it like this, where we truly have this this thing reduced, where all these coefficients are 1, the diagonal are all 1, everything else is zeros in the coefficient part, and then I have the constants here. What this means is that x equals 2, y equals negative 3, and 1 equals 1. Okay, so that's, we read that out directly and we'll report it as a coordinate tuple. So the assignment that I'd like you to do is there's a worksheet with 3 problems on it that's posted, and I'd like you to do those before Friday's lecture. That would be great if you could accomplish that, and we'll be doing more in class along these lines. I also recommend that you read the text, because the text has some examples of this as well, chapter 3.2 and 3.3.